Okay, so hello everybody, and welcome to this exploration of one-dimensional projectivities. So, projective geometry is, as you can probably guess from the name, all about projections, and amongst the simplest variety are these kind which just project the line to itself. However, there is actually quite some intricacy in this family of mappings, and they can be divided up in a fairly interesting way. So what we're going to look at today is what are the different types of one-dimensional projectivities, how can we construct them, and what kind of properties do they have. So with a perspectivity, you have some object, say this blue point, and you have some so-called centre of perspective, just some fixed point somewhere. And then you draw a line from the centre of perspectivity through the object, and you see where that line intersects with the thing you're projecting onto. So in this case, we're projecting from this lower line to this upper line. And that black dot there represents the image. So we can see how the image moves as the object moves. It's almost as if you're looking at the object from the centre of perspectivity and seeing where its shadow is cast on the other line. But we're more interested today in projections from the line to itself. So how do we work out those? Well, if we place another centre of perspectivity, we can do another perspectivity, back through here, back onto our original line again. So let's just find a place where this returning ray hits the line again, and now we have our final object. So just to emphasize this, let me make an arrow. So this is the object, and this is its final image. And now as we vary the object, we see how the image changes on the line itself. So what we actually have here is a mapping from the line to itself. These are the kind of things we're going to be interested in today. What kinds of projections are there from the line to itself? So you can see we've already got some fairly interesting dynamics. The image has been projected to the right until we pass this line. Now it's been projected to the left. However, it sort of slows down and gets closer and closer to the object as we reach the intersection point of the two lines. And now the object is being projected to the right again. So there's quite a lot of richness of possibility in these different systems. Okay, so one nice way to visualize how a projectivity is working is to plot a curve like this, which shows the amount of displacement to the right of the image from the object. That's given by the perpendicular distance from this black line that the object's running on to this blue curve. So it's slightly slanted, but it's basically like a plot with Cartesian coordinates showing how much and in what direction the image is displaced. So in this case you can see that this blue line is crossing our black line twice, and those are corresponding to the two invariant points where this projection is mapping the point to itself. So one fairly neat way to start to classify one-dimensional projectivities is in terms of how many invariant points they have. And people have come up with names of these different things. The names will seem familiar to those who know about conic sections, but it's best just to think of them as generic names. So this particular projectivity here is called a hyperbolic projectivity because it has two invariant points. That's the definition. If it only had one invariant point, it would be a parabolic projectivity. Let's see if we can make one of those by varying the centers of perspective. It looks like there's only one fixed point in this projectivity. So that would make it a parabolic projectivity. And then if we have a projectivity with no invariant points, when the image never gets mapped to the object, well, that would be a so-called elliptic projectivity. Now they're very interesting because they're not so easy to construct, and in fact there are frameworks of projective geometry where they don't even exist. The other kind of projectivity is not very interesting at all. It turns out, according to the fundamental theorem of projective geometry, that if you have more than two invariant points, every point has to be invariant. So if you have 3 points where this blue curve crosses this big black line, then the blue curve has to be equal to the big black line. So it turns out that one very systematic way to think about this is to actually have the projection points on the lines. So we're going to think about a perspectivity from this line to this line. And the centre of perspectivity is going to be this point here, B dash. So let's colour it in purple. And now after we do that, we're going to do a second perspectivity back from this top line to the bottom line. And for that, we're going to use this centre of perspectivity here, which I may as well colour violet. So then, how do we do this? Well, to start with, it's quite useful if we do some kind of cross joins. So we join this centre with the rightmost points on the top line, and similarly the centre on the top with the rightmost point on the bottom. And that gives us this additional point which we can mark out. And we can do it again from this centre to the leftmost point, and from this centre to the leftmost point, which is in the centre itself. And we get a second meeting point. Now if we draw in this line, this turns out to be a fairly important line for this perspectivity. So now let's have a look how this actually works. We can put a variable point on our bottom line. This blue one here. And so firstly we're going to project it through the centre of perspectivity B. And we'll see where that gets projected onto this new line which we've just drawn, which is really the intermediary line. And now we see where that point gets projected back with centre of perspectivity A, and we mark where that meets this top line. And there we have it. You can see how this object is getting mapped to this image. So what is this mapping doing? Well, look, it's sending B to A dash, and it's sending A to B dash, it's sending B to A dash, and it's sending C to itself. So not only is this projectivity defined across all of the line, it actually juxtaposes or swaps around the points as we've placed them down. So we can literally do permutations of a set of points via this construction method. But you might say, well, I thought we were interested in projectivities from the line to itself. This is a projectivity from a line to another line. And that's true. But we can easily get around that just by doing a simple projection back again. So now we've done this projectivity from the bottom line to the top, setting the blue point to the red. Well, we want to get back again. And so to do that, we do a similar kind of method. This time I want a sort of identity mapping. So I'm going to use these leftmost points as the centres of perspectivity. And once again, you use a similar method. You find these cross joins from A to B and A to C. Each of those cross joins gives you a point. You link those cross joins together. That gives us your axis of perspectivity. And now we're interested in how this red point is going to get projected. So the first perspectivity we do on it is downwards to the violet point on the bottom line. So we just draw a line down like so. And now we see where this intersects with our green line, which should be here. And now for the second point, we use this top point of perspectivity here. And we just see where that projects down onto the ground line again. Okay, so let's just clean this up a bit. We'll get rid of these green lines. And all being well, yes, you see, this projection just does just what the original one did, except it's mapping the line to itself. So it sends A to B, it sends B to A, and it sends C to C. So this is doing exactly the kind of permutation that we want. Now, why is this important? Well, one of the main reasons is because according to the fundamental theorem of projective geometry, if you know how a projectivity works on 3 points, in other words, how it sends 3 points to their images, then you know there's only actually one projectivity that's like that. So in other words, specifying 3 objects and their images is enough information for you to be able to tell what's going to happen to every other point on your mapping. And what we have here is a systematic way of setting up the different permutations from 3 points to 3 points. So for this kind of setup here, where you do any kind of permutation you like, you see I swapped A and B around in the first step by having one centre of perspectivity at A and one centre of perspectivity at B. And then I just did the identity mapping to get back. So I only really did one active projectivity, which essentially had the effect of swapping A and B around. And that was actually composed of 2 perspectivities. So hopefully you can see that each step, either going from the bottom to the top or the top to the bottom, is really 2 perspectivities, because we're using 2 centres of perspectivity to do each. Now, it turns out that there's a well-known result which says that you can only get identity, hyperbolic or parabolic projectivities if you only use 2 perspectivities. Now, I know we are using extra ones to get back to the line itself, but that's just an identity mapping. The fact of the matter is you cannot get elliptic mappings this way if you only use an identity mapping to get back. But what is the actual effect of this mapping here? Well, let's think about it. We're swapping A to B and B to A, and C is staying the same. Well, a sort of group theorist might look at it like this. We're sending A to B, we're sending B to A, and we're not moving this other point. That's just staying fixed. So it turns out we can get lots of mappings, but one of them that's quite difficult to get, and perhaps indicative of it being causing elliptic projectivities, is this kind of mapping here, where A goes to B, say, B goes to C, and C goes to A. It's kind of like period 3 rotation or orbit. So can we create such a thing here? Well, yes, we can. All we need to do is join together 2 different permutations like this, one acting on A and B, and one acting on B and C. Okay, so now we're doing this different kind of permutation to get back to the bottom, different kind of projection, which is going to have the effect of swapping B and C around. And hopefully this should give us our kind of triangular, our kind of period 3 rotation kind of permutation that we want to have. So how do we construct it? Well, this is one of our centres of perspectivity. So we'll join that to the leftmost point on the other line. Similarly from top to bottom, that gives us 1 cross point. Now we join C to the topmost point on the upper line, and similarly for the bottom, and that gives us our other cross points. Just a little off screen. If we zoom out a bit. There it is. Now we can link those 2 points together to give us our new intermediary line. Okay, so What we're interested in now is how this red point, how is that going to get affected by this mapping? Well, firstly we do a perspectivity on the bottom point, and we see where that crosses this intermediary line. And then we do a second perspectivity using this top point as a centre. And we get the final image, which is here. Make it a nice green colour. And we can draw an arrow from the red to the green. Let's get rid of these messy lines. So this is our mapping, and what's it affecting? Well, look, it's sending B to A, it's sending A to C, and it's sending C to B. So it's actually a permutation on these three letters. Quite remarkable, really. Okay then, so let's actually visualize how this projectivity is working. We can get rid of a lot of these lines now. Okay then, so now we can basically see, we can actually see what this curve looks like. So it's similar to before. What we're seeing here is this curve, which is showing us, essentially we've got our initial object here. I'll do an arrow to the final object just to make this clear, because I know it's gets a bit complicated. Essentially, we're just interested in how this blue point gets mapped to this green point. This sort of magenta curve at the top and bottom, this is showing us how much displacement there is from the object to the image, excuse me. So when the curve is above, it means the displacement is to the right, and when the curve is below, it means the displacement is to the left. Now I find this really interesting because this curve never crosses the x-axis, and yet it's able to change its sign. I mean, over here it's mapping the object to the right, and over here it's mapping the object to the left. But what's changing? Well, it must have somehow gone to infinity in some sense and switched its direction that way. And we can also vary, I think if we... So it turns out we can say rather a lot about the dynamics of these elliptical projectivities. The thing is, we know that they have a period 3 orbit. So let's assume that the system does have another orbit of period other than 3. Let's say k. So in other words, if we apply this mapping k, if we apply this projectivity k times to the system, it should alter the point, it should return the point to itself. Well now, The system is an elliptical mapping, so it has no invariant points. So we know already that it has no period 1 points, if you like. So we know k can't be 1. The other thing is, if we compose this mapping with itself 3 times, what we end up doing is getting the identity. And this is a remarkable fact, but it must be true, because when you apply the mapping 3 times, each of these points moves around the triangle, and as they do so, they all end up returning to their initial positions after 3 updates. So that means that composing this elliptic projectivity 3 times of itself gives you something with 3 invariant points. What do we know about things with 3 invariant points? Well, according to one of our axioms of projective geometry, or indeed according to the fundamental theorem, we know that 3 invariant points implies every point is invariant. And now we can see how all the other cycles are eliminated. So we can call this a thing that you get by, let's call our elliptical projection f. So FFF, that's what you get if you apply this function 3 times. Well, we know that's the identity. So we know that f itself cannot contain any period 2 orbits, since if it did, those orbits, let's say, would go from D to E and back to E, and back to D again, and so those would not be invariant points in FFF. Similarly, if we had any other point which is on a higher period orbit, say a 4 orbit or a 5 orbit, well, 3 steps isn't enough to return that point to its own position. So again, we must have that FFF is not the identity, but we know it is. So finally then, the other case is, what if you don't have orbits, but what if you've just got this one triangle and all the other points are just strung together in a long line? Well, that can't be so either, because, you know, all pointing in the same direction or something. That can't be so either. These infinite linear chains in the same direction can't occur, again, because FFF has to be the identity. Basically, what we're doing is we're looking at the injections, the injective mappings from the set A, B, C, to the sets A, B, C, D, E, F. Okay, excuse the chronic handwriting. It's not easy to draw with a mouse. Okay, but why is that? What is an injective mapping? Well, an injective mapping is a mapping where we're not allowed to send 2 elements to the same place. Okay, so we wouldn't, say, be allowed to map A to A and B to A. That would not be allowed. So every element, so no 2 elements can be sent to the same element, and that's our only rule. So why are our 3D projectivities so represented? Well, again, it comes from this fundamental theorem of projective geometry, that if you know how 3 points are projected to 3 points on a 1D projectivity, then that essentially specifies the whole projectivity. So our 3 points, if we're projecting from a line to itself, our 3 points A, B and C, they might land on points A, B or C, or they might land on 3 other sort of different points, which we can just call D, E and F. So how many one-dimensional projectivities are there from a line to itself? Well, it's the number of injective mappings from 3 elements to 6 elements. So our first element can go in 6 different positions, our second element in 5, and our third in 4. So it's 6 times 5 times 4, which is 120, I think. So there's 120 different injective mappings. But the thing is that there's actually not that many distinct ones. And the only one which you need more than 2 perspectivities to make is the triangle one. And that's clearly elliptical. So we found the only elliptical mapping. How do we separate the others? How do we separate the hyperbolic mappings from the parabolic mappings? Okay, so it turns out that quadrangles can be very useful for working out things to do with projectivities. In fact, they can help us to differentiate between the parabolic and the hyperbolic projectivities. So, a complete quadrangle, that's just generated by getting 4 points, no 3 of which lie in a straight line, and then drawing the 6 possible edges connecting pairs of points. And to get a quadrangular set, you just take a complete quadrangle and then you sort of section it. You slice across it with a line, in this case this yellow line, and you see where this yellow line intersects with each of the 6 edges. So that'll give you 6 points on a line, and that's what a quadrangular set is. So if you look at the top right here, there's some kind of algebra, and what it says here is on the left hand side of this sort of algebraic expression, it's describing the quadrangular set. Notice that there are 3 bracketed off pairs of letters. They correspond to the 3 pairs of opposite edges, well, the 3 pairs of points generated by opposite edges of the complete quadrangle. So we'll say that a pair of edges are opposite when they don't have any vertices of the quadrangle in common. So for example, A and D are generated by these edges here, and those edges don't have any common vertices in the quadrangle. Similarly with B and E, and C and F. So this is standard notation for, well, some standard notation for writing a quadrangular set. What about this thing on the right? Well, this is about projectivities. This is what's of interest to us today, because what it says is that whenever we have such a quadrangular set, we have this condition on the right, it's equivalent, logically equivalent, and it says that there's a projectivity that sends A to B, E to D, C to C, and F to F. So in general then, when C and F are distinct, this is going to be a hyperbolic projectivity, one with 2 invariant points. Well, that's all well and good, but how do we actually construct it? Well, what we do is we look at this line through F, and we use that as our intermediary line, and we do a projection through one of the vertices, as using one of the vertices not on that line as a point of perspective, and then using the other one as a point of perspective. And you can see how this does indeed give us this projectivity. You can see how it's working here with this blue object and the arrows pointing to where it gets mapped to. So does this behave as it's supposed to? Well, it maps A to B. So far so good. Does it map E to D? Yes, it does. Does it map C to C? Yes. And does it map F to F? Yes, it does. So it has all the properties that we need. So the quadrangle is intimately associated with the existence of projections, because this is a if and only if kind of statement. So how does this result actually help us differentiate between parabolic and hyperbolic projectivities from a line to itself? Well, it's all about this C and F. You see, on the expression on the right, it's naturally saying that C and F are both invariant points. So in general, this will be a hyperbolic projection, one of those with two invariant points. I mean, it's obviously not the identity, because we can see that it's actually doing stuff, but the thing is though, there is a special case which does give us a parabolic projectivity, and that's when C and F coincide. So I don't know if I can warp this quadrangle to make, there we go. Nearly. Oh, it's very sensitive. Okay, so now we have C and F coinciding, and now what we have is a parabolic projectivity, one which only has a single fixed point, and that's where C and F meet. And again, from the fundamental theorem of projective geometry, since this expression on the top right here is using 3 or more letters and describing how they are projected, it's enough information to completely specify the system.